Now what we're going to look at is something that kind of goes beyond um, looking at these very simple molecules where we can just talk about the overlap of orbitals. And this is where we get into the hybridization of atomic orbitals. And so this is kind of a model we use to help explain the behavior and explain the properties that we see. And so hybridization is just this hypothetical blending of orbitals. The number of hybrid orbitals must equal the number of atomic orbitals. And we've already talked about atomic orbitals. That's the 1s, and 2s, and 2p. And what we're going to look at is that the electron geometry, that we can actually look at that, relate that to these hybrid orbitals, and so how we kind of understand the connection between those. We kind of started by looking at Lewis structures to find the electron geometry, but in reality it was the electron geometry that helped us figure out what the hybrid orbitals were shaped like and what they were, how they were arranged. So let's look at methane as a simple example. So what we see is that when we look at the valence of carbon, we have 2 electrons in the 2s orbital and 1 in each of the 2p orbitals, and we have a whole empty orbital. So we actually only have 2 unpaired electrons when we look at this. And so what we would expect is that that would form CH2 because we just need to pair up those electrons. But we don't. We actually see CH4 forming. And so we have to be able to kind of justify that with understanding what we know about the electron arrangement or the electron configuration of carbon, how we're forming 4 bonds, since we only have 2 unpaired electrons. And what we see is that, well, this shouldn't bond because those are paired and they're happy the way they are. So what we go to is what we call an excited state configuration. So we looked at this a little bit when we looked at the hydrogen atom. We talked about it being in the ground state and its electron in the ground state, that n equals 1, getting promoted to the 2, absorbing energy, going back and releasing energy when we looked at Rydberg's equation. Well, we can actually have excited state configurations for any atom. And so when we think about this, what we say is, well, let's imagine that carbon goes into an excited state configuration. So that electron in the 2s orbital is actually promoted to a 2p. Now remember, this is not going to happen in the ground state. Okay, we're not going to see this in the ground state. This is because it's an excited state. And so this would explain why we get CH4, that we get 1, 2, 3, 4 unpaired electrons, and we could form this bond. The next problem comes in is because we have these 2p orbitals. Remember, those are all perpendicular to one another on the x, y, and z axis. And we know that when we look at a tetrahedral molecule like methane, CH4, we don't see 90-degree angles. We see angles that are 109.5. So while this model explains the number of bonds, it doesn't explain the geometry of the molecule. So this is where hybrid orbitals come in. So we think of this as this blending. So what we're doing is we're taking our 2s and our 3 2p orbitals, we're blending those to form the sp3 orbitals. Now we have 4 equivalent orbitals, they're degenerate, they all have the same energy, each with an unpaired electron. And what that lets see is that we're going to get 4 bonds to form with each overlapping with one of these hybrid orbitals. And all the orbitals are degenerate, so we don't see any differences between, say, the 2s and the 2p orbitals. It also lets us see the 109.5. So this is just a model that helps us understand what we're seeing about a molecule. So when we look at the energy of this, what we see is the 2s orbital and the 2p orbitals, they blend, and we get something that has, we call it sp3. It's closer to the 2p orbital energy because there are more p orbitals in there and only the one s orbital. But the key is that we get these 4 identical orbitals that form. Now, when we start to look at the bonds and look at the overlaps occurring, we can explain it based on what we actually see experimentally. So now when I'm looking at my CH4 molecule, this is similar to what we looked at with the H2 and F2 and HF. The difference is now, instead of looking at atomic orbitals, we have to think of these in terms of hybrid orbitals. So what I've got here is my hydrogen, the 1s orbital of hydrogen. It's got a single electron bonding with the sp3 hybrid orbital of the methane, rather than looking at the s or the p orbitals of the carbon. We're looking at the hybrid orbitals of the carbon. So when we go to something like NH3, also has tetrahedral electron group geometry. Remember, there's 3 bonds in a lone pair. What we see different here is now, instead of having 4 sp3 hybrid orbitals involved in the bonding, we only see that 3 of them are involved in the bonding, and one of them is the lone pair. We don't need to form a bond because we have the bonding electrons. We still need to look at the hybrid orbitals, because if we look at just these 2p, then what we're seeing is that these would all be 90 degrees from one another. And when we look at NH3, we don't see 90-degree bond angles. We see 109.5, well, slightly less than 109.5 degree angles. We continue this on, we get sp2 hybridization, which is looking at the s orbital and two of the p orbitals. We don't have enough electrons to fill that empty p orbital, so what we get is trigonal planar. So sp2 hybridization is associated with trigonal planar. And so we see that we have the overlap of the boron. These sp2 hybrid orbitals on the boron overlap with the 2p orbitals on the fluorine to form that bond. Then we can go on to sp hybridization, and we see this associated with linear molecules. So we don't need to fill up our p orbitals. We'll have empty p orbitals, but we'll have two sp hybrid orbitals because they're a mixing of the s and the p. But we need to do that to explain the bond angles in the actual molecules. So looking here at BeCl2, which is our example, the Be is sp hybridized, overlapping with the 2p or the 3p orbitals of chlorine to form that bond, and we have a linear geometry. So what we see is that once we know the electron pair arrangement or the electron group geometry or electron pair geometry, whatever you're calling it, we see that if it's linear, we're going to have two sp hybrid orbitals. If it's trigonal planar, we'll have 3 sp2, and if it's tetrahedral, we'll have 4 sp3. So these correlations always go together regardless of the identity of the element in the middle or the terminal atoms. Once we know the geometry, which we figured out from our Lewis structure, we can know what hybrid orbitals are forming on that central atom, and then we can start to look at the overlap that's happening to form those bonds. So is it an sp orbital and an s orbital forming the bond, or an sp2 and an s orbital, any of those things, but what we're looking at, it's always associated with the same geometry. Now, you will see some hybridization schemes that kind of talk about sp3d and sp3d2. We are not going to cover those. It gets into trigonal bipyramid and octahedral geometries, but there are some issues with how those could actually, the model of blending that we kind of propose doesn't really work out because of differences in energy levels.